That was the first time in my entire life someone has pronounced my name correctly, introducing me. So I feel good to be home, where people can pronounce my name. All right, so I'm here today to talk to you about the legacy of Go. When we think about legacy, I like to think of this quote. It is up to us to live the legacy that was left for us and to leave a legacy that was worthy of our children and of future generations. This is by Christine Gregori. To me, this means that legacy goes both directions. We inherit a legacy that we need to live up to, and we pass a legacy down. So with that in mind, I'd like to take us back to the time before Go. So join with me as we get in our... Oh, good. All right. You can laugh. It's okay. It's the end of a long conference. So we're getting in our time machine, and we're going to travel back to the year 1950. So in the year 1950, people were becoming uneasy how each new computer spawned its own programming language. At the time, programming languages were provided by hardware manufacturers and differed from model to model. The first language to be consistent across models was Fortran, but it was still only uniform for its manufacturer, IBM. A committee was formed to design the first truly universal, machine-independent programming language. All right, and this was on the cover of one of the computer magazines in that year. And so, in 1960, in Paris, 13 computer scientists met for an unprecedented meeting with the goal of developing such a language. There were 6 delegates sent from America and 7 from Europe. Alan Perlis, one of the delegates, said, "The meetings were exhausting, interminable, and exhilarating. One became aggravated when one's good ideas were discarded, along with the bad ones of others. Nevertheless, diligence persisted during the entire period. The chemistry of the 13 was excellent. And the result was Algal." Who here programs in Algal? Who here has heard of Algal? Oh, that's really good. In the US, it's not as good. All right. About this language, Tony Hoare wrote, "Here is a language so far ahead of its time that it was not only an improvement on its predecessors, but also on nearly all of its successors." In spite of that statement, Tony Hoare, along with Nicholas Wirth, went on to create a successor of Algal called Algal W, which in turn led Wirth to create Pascal, initially published in 1970. Independently, CPL was created at the University of Cambridge as the Cambridge Programming Language. It led to BCPL, or Basic CPL, a much simpler language based on CPL. At Bell Labs in the United States, Ken Thompson and Dennis Ritchie created B, based mainly on BCPL, and shortly after its successor C. And so at that point, there was a continental shift between languages as a result. In Europe, the Pascal branch flourished, with many successors, including Modula and Oberon. C proliferated in the US, inspiring and enabling C++, C#, Java, as well as JavaScript, Python, PHP, Perl, and many other languages. So by 2007, there were dozens of languages that existed that can all trace their roots back to their one common ancestor, Algal. Now we're going to travel back to 1964, when another branch of computer programming languages was created. This begins with a man named Douglas McElroy, who, back in 1964, came up with the idea that became Unix pipes. This is the note that he typed up back in 1964. And it reads, "We should have some way of coupling programs, like garden hoses. Screw in another segment when it becomes necessary to massage data in another way. This is the way of I/O also." And I'm going to tell you the story in his own words. So over a period of 1970 to 1972, I'd say from time to time, "How about making something like this?" And I'd put up another proposal, another proposal, another proposal. And one day, I came up with a syntax for the shell that went along with the piping. This is like, if it could go wrong, it's going to go wrong. So what else is going to happen next? We'll find out. This is going to be an exciting talk. All right. So he came up with a syntax for the shell that went along with the piping, and Ken said, "I'm going to do it." He was tired of hearing all this stuff, and he said, "I'm going to do it." He didn't do exactly what I had proposed for the pipe system call. He invented a slightly better one that finally got changed once more to what we have today. He He put pipes into Unix, and he did it all in one night. So now we step forward to 1978, still on the same branch, with a man named Tony Hoare. By 1978, there were many methods proposed for communication and synchronization in the context of multiprocessors. Shared memory was the most common communication mechanism. Tony Hoare published a paper which changed everything. It was decades ahead of its time. He called his paper Communicating Sequential Processes, or as it's better known, CSP. And to break these down, I would like to talk about each of them individually. A process is a unit of execution. They run sequentially, each of them as an ordinary single-threaded program. And they communicate. How do they communicate? They communicate over unbuffered channels. There's no sharing of memory, there's no threads, and there's no mutexes. Hoare's communicating processes are more general than typical Unix shell pipelines because they can be connected in arbitrary patterns. 3 different branches of languages emerged from the CSP paper. The first was Occam, which was written shortly after, and it was advised by Hoare. Next came Erlang, which focused on the functional side of CSP and used mailbox to communicate between processes. And then Bell Labs was inspired by this and created a series of languages, New, Squeak, Aleph, and Limbo. And so each of these 3 branches culminate in Go. Go is the first language that can claim heritage of both the US and the European branches of language design. It really unified these 3 branches. This has caused some to criticize Go, calling it a language stuck in the 1970s. And I think what is old is new again. So I'd like to talk about kind of how things have transpired over that time. I talk about them in the sense of waves. Each of these waves lasted for a long time, and each of the waves starts after the other one begins, but they overlap each other. So the first wave is what we saw in that picture, the Tower of Babel, where there was a lot of diversity of languages, and diversity of thought, diversity of opinion. The reaction to this was to standardize things. And so standardization of languages occurred over decades. By the 2000s, things really started to stagnate. They converged into 2 camps. There was the Java JVM, C#, CLR, and C++ camp. And all of these are really similar, that they're fast, but they're also really complex. And it requires a lot of time to really become proficient in these languages. So a reaction to that is wave 3, scripting languages. And they emerged in prominence as a reaction to the complexity and pain of the wave 2 languages. But these languages are fast and loose. They're developer friendly, but they lacked performance and safety. And so the 4th wave was a reaction to all of these. It's Go. Go reacted to the complexity and pain of the languages and a reaction to the fast and loose nature of the scripting languages. Go restored the simplicity and brilliance of early languages, but with the added safety and developer friendliness of the modern languages. In a very real way, Go revived many ideas whose time is finally ready. So I think that Go feels like a language from the 60s, 70s, 80s, 90s, aughts, and teens. It feels like this because it's composed of many ideas from the past 60 years. I'd like to talk about 3 specific features in Go and the 4 languages whose ideas they originated in. Many of these ideas were forgotten until Go restored them. So we're going to jump into our DeLorean and travel to 1988. The first of these features is simple, readable structure and syntax. And Go takes this from Oberon and C. So this starts with Nicholas Wirth, who was responsible for Algal W, Pascal, Modula, and now in 1988, his latest language, Oberon. All right, who here programmed in Oberon? Raise your hands. All right, for everyone else, this is what Oberon looked like. I'd never programmed in it before seeing this, but when I did find this, I was shocked about how simple it looked, how straightforward it was, and I was shocked how familiar it looked. This is because Go structure was taken directly from Oberon. Not only the structure of our programs, but also our declaration structure. In Go and Oberon, declarations are always left to right. The name always comes first, and then the type, and optionally a value, as opposed to C, where the type comes first. A lot of people look at Go and ask, why did we flip the C syntax, mistakenly thinking our structure came from C? It didn't. It came from Oberon. Well, the structure came from Oberon. The tokens Go uses come from C. And there's not a lot to this point, and that is the point. The structure and the syntax is simple. There's no inheritance, there's no levels, there's not a complex scope system. They're as simple as possible, but not simpler. You can see how Go took the nice, simple structure of Oberon, but removed the clunky syntax and replaced it with C's much more elegant and familiar syntax. And the end result is a very readable language. Now we step forward to 1989 to talk about our next feature, concurrency, with NewSqueak. With this, I mentioned it was Bell Labs, but it was Rob Pike at Bell Labs who was the one who pioneered this work. And he built a language along with a coworker called NewSqueak. NewSqueak was a research language. It's called NewSqueak because it's the successor to Squeak. Squeak was a toy language that was written to communicate with mice, but you couldn't build a whole program with it. And so they took the ideas from Squeak and they turned them into NewSqueak, which you could build a full program with. Syntactically, it was very similar to C, but like CSP, it used channels as rendezvous points for processes. And so here's an example. And we're not going to step through all of it, but I want to show you what NewSqueak looked like. It should look pretty familiar to Go programmers. There's things you can identify. Anyone point out something that they think is interesting in this? That was not rhetorical? What? Colon equals. That's right. It does have colon equals. Anything else? Channels. What's interesting about these channels? They are a type. But more interesting, they're a parameter, which means they're first class. So I'm stepping forward a little bit to the next part of the prime sieve. Unlike its predecessors, CSP and Squeak, NewSqueak treated communication channels as first-class objects. You could store them as variables, you could pass them along as arguments to functions, and you could send channels across channels. Also introduced for the first time was the receive operator, the arrow, and then the channel that it's coming from. It's really interesting when you put the two of them side by side. Go's concurrency approach is pretty much exactly that of NewSqueak. The way you work with channels and processes, which we've now called Go routines, is the same. NewSqueak also used select, which looks very similar to Go's select. So you can see how clearly the fundamentals of Go's concurrency were established in NewSqueak over 25 years ago. Go took these ideas and improved on them, making them production ready. Ryan Dahl, the creator of Node.js, wrote, "I like the programming model of Go. Using Go routines is so easy and fun. If you're building a server, I can't imagine using anything other than Go." So now we're going to travel to 1965 for our final feature, which is fundamental object orientation and small talk. Object orientation, or object-oriented, existed long before C++ and Java. But we have at least one or two generations of computer programmers that's the only kind of object orientation they've ever worked with. So I'd like to step us back to a more fundamental definition of it, which is that object orientation is two things. It's procedures attached to data objects and reusability of procedures. And we're going to step through each of these separately. The procedures in data one first. This comes first from Simula. Simula was the first object-oriented programming language. It took Algal and it added to it objects, classes, inheritance, and subclasses. And it was very influential in the development of Smalltalk and all following OO languages. Dan Ingalls, who implemented Smalltalk, wrote, "Simula changed from the procedural view. They flipped it around to the object-oriented one, which is that within every type of object, you have all the procedures that work on it." In the 1980s, this led to Smalltalk, where everything is an object, and objects are only communicated via the sending of messages. Alan Kay, the creator of Smalltalk, wrote, "I did make up this term object-oriented, and it was a bad choice because it underemphasized the more important idea of message sending." So I'm going to talk a little about where the procedural reuse part comes. We're going to jump to 1989, and there's 2 publications this year that we're going to talk about. The first is Dan Engel's book, which we've already quoted from, Object-Oriented Programming. And he writes, if any part of a system depends on the internals of another part, then the complexity increases as the square of the size of the system. But what is inheritance? Except for lots of internal dependencies. Anyone who's used an OO-based language knows that as the program grows, the complexity grows immensely. It leads to lots of spaghetti code. It's really hard to manage. Also in that year, at HP Labs, they wrote a research paper called Interfaces for Strongly Typed Object-Oriented Programming, in which they set out to provide the benefits of a module interfaces found in languages like Ada and Modular 2, while preserving the expressiveness that give untyped object-oriented languages like Smalltalk their flexibility. What they came up with was very similar to Go. Now, the Go team was unaware of this paper at the time they implemented interfaces. The paper was shared with them later due to the clear similarity of the 2 approaches. Because Go does take a very similar approach, but it improves on the idea in the paper that in Go, interfaces are implicit, which decouples Go applications and gives them immense flexibility. Go's approaches, so Dan Ingalls wrote, when you try to break a complex problem down, you want to try and break it down in as few parts as you can, and you want them to be as independent as possible, or as they can be. Go's approach of interfaces and methods is as independent as possible. Any type can satisfy any interface as long as the right methods are added. An interface can be defined before or after the types that satisfy that interface. It just works, and it works well. So what is GoOO? GoOO is methods that provide message sending mechanism on any type, and interfaces that provide reusability through dynamic dispatch polymorphism. So in Smalltalk, OO is about message sending, and in Go, our interfaces permit methods to be used as freely as Smalltalk's messages, but from within a typed language. So we've talked about all these different languages and features that preceded Go. Now I'd like to kind of walk you through the process that we used as we looked at all of these as inspiration and compiled them into Go. So we're going to jump in our TARDIS and travel back to 2007, for the moment that Go was born, which is during a 45-minute C++ build. Rob Pike, and I'll read his own words. He said, back around September 2007, I was doing some minor but central work on an enormous C++ program, one you've all interacted with, and my compilations were taking about 45 minutes on our huge distributed compile cluster. An announcement came around that there was going to be a talk presented by a couple of Google employees serving on the C++ Standards Committee. They were going to tell us what was coming in C++ 11. In the span of an hour at that talk, we heard about something like 35 new features that were being planned. At this point, I asked myself a question. Did the C++ committee really believe that what was wrong with C++ was that it didn't have enough features? Surely it would have been a greater achievement to simplify the language than to add to it. And so Rob returned to his desk with his office mates. They started another compile, and they started thinking about the question, what should a modern practical programming language look like? By the time that 45-minute build was done, they already had a whiteboard full of ideas. Most of you are probably familiar with the story. Who were his office mates? It was Robert Griesmer, who comes from Europe. He's Swiss. And he studied under Nicholas Wirth. He knew Smalltalk. He knew Pascal really well. He was one of the authors of Modula 2. He really understood Oberon. And the other was Ken Thompson, who comes from the US and worked with Rob at Bell Labs, was behind B, C, and Unix. What they followed, we call an evolutionary process of language design. In Rob's words, he said, we built from scratch, borrowing from C only minor things like operators and brace brackets, and a few common keywords. And of course, we also borrowed from other languages we knew. And this is just a sample of some of the many languages that they had expertise in that inspired Go. In fact, I would claim that there's never been a set of language designers with a broader or deeper knowledge of design expertise than these three. They had a rich knowledge of what came before, and they knew just what to cherry pick. They also had the advantage of hindsight. Here was a chance to fix the things that they felt they could do better on. So they followed 4 principles. We're going to talk about each of them. The first principle is evolution, not revolution. The idea that most ideas aren't new. They come from previous ideas. And that new languages should consolidate, not invent features. The second principle is waiting for good design. That no is temporary, but yes is forever. There's many instances of this throughout Go's history. The general idea is that when you're designing a language, there is no undo. If you say no today, you can always say yes tomorrow. But if you say yes today, you're stuck forever. As Josh Block, the author of Effective Java, writes, when in doubt, leave it out. The third principle is that of consensus-driven design. This leads to everything being as simple as possible, but no simpler. Ken writes, when the 3 of us got started, it was pure research. We started off with the idea that all 3 of us had to be talked into every feature in the language, so there was no extraneous garbage put into the language for any reason. Tony Hoare writes that there are 2 ways of constructing software design. One way is to make it so simple that there are obviously no deficiencies. The other way is to make it so complicated that there are no obvious deficiencies. So Go took one approach, and most languages take the other. And the fourth principle is that of rapid iteration. That when you're in the design phases of language, you need to make frequent and sometimes dramatic changes. Go forward with that expectation and build your process around it. And we did that. In the several years leading up to Go 1, we made major changes. We even built a tool, GoFix, to enable us to make these dramatic changes. So now I want to talk to you about Go today. So in 2019, there's no time machine to get here because we are here. So I want to talk to you about how Go continues to make changes. These 4 principles worked really well at the beginning of the language, before we had a stable release, before we had any adoption. Our situation is now very different. We can no longer fit all of our contributors around a whiteboard. In fact, we can't even fit them all in a room this size. So I'd like to share with you now how the Go project makes changes today. We still follow our principles, especially the second and third one. So our principle, waiting for good design, which seems to imply that it's a passive activity, but this is far from the truth. Really, it means that until we're very confident we have the right approach, we don't accept changes. What this also means is that the default answer to everything is no. The cost of yes is very high. There needs to be an overwhelming reason to do it. Yes to one thing means no to everything else. Nicholas Wirth wrote, a primary cause of software complexity is that vendors uncritically adopt almost any feature that users want. People seem to misinterpret complexity as sophistication. The incomprehensible should cause suspicion rather than admiration. We're taking a long-term view of Go, designing it for the next decade or 2 or more. Most projects operate on a much shorter time frame, and as a result, typically accept the first passable solution. Over time, this has trained people that if an idea is good, it will be accepted, or the inverse, that only bad ideas are rejected. As a result of our longer-term view, it's not uncommon for people to struggle when contributing to the Go project. Many feel personally rejected when their ideas are not accepted. Or perhaps worse, they feel unqualified. I remember feeling this way. Several years ago, I created Hugo, a website engine, which over time became the #1 user of Go templates. And through the process, I found several issues. In spite of this, I felt very unqualified to even report these issues, as I thought the experts who created the libraries clearly knew more than I did, and I couldn't add anything to what they knew. So at the first or second GopherCon, I was in the lunch line, and I happened to be standing next to Russ Cox, who I'd never met before. And we began talking, and he strongly encouraged me to report these issues and let me know how much they really needed feedback like this. In spite of that encouragement, I was too scared, and I didn't do it. Fast forward a few years, and I'm now a member of the Go team, and I've learned a lot from that experience. One thing I've observed, that there's one thing the long-term members of the Go team do better than others, and it's probably not what you think. The long-standing members of the Go team have grown very accustomed to hearing no. Proposals from members of our team have a very high rejection rate. In fact, I believe it's even higher than those from outside of our team. We've just learned that each no is one step closer to hearing the right yes. Right? And I say that, I think of Ian Lance Taylor, who is sitting in the back of the room, and he's not going to like that I'm doing this, but he has spent the last 10 years working on generics and submitting proposal after proposal, right? Because he knows that when we finally do get the right thing, it's going to be the right thing. And it's worth going through the process to do it right. So because we hear no so often, we're very sympathetic of anyone who's feeling rejected. My message to you today is that you are valued. Keep trying. You are a critical part of creating Go for the next decade or two or more. Earlier this year, Russ Cox gave an excellent talk about the process we use to make design changes to Go and how it's evolved. In his talk, he discusses the 2 steps of experiment and then simplify, and we iterate over these steps. This process is not built for speed, but correctness. We spend a lot of time experimenting and simplifying, refining our ideas until they are right. All right. If everyone just looks this direction, everyone will have one that's, I don't know, AV people want to? All right, cool. You are part of the great experiment that is Go, and you're a critical part of the process of continuing to build Go. I'd like to share with you 3 ways which you can contribute to Go. The first way is simple. The first step most of you already have taken, it's you use Go. And as you do that, you will no doubt find problems. When you do find problems, write down your experience and publish them as experience reports. The second way you can help is have ideas. I'm sure you've already had plenty of ideas. Then write them down as a proposal. And as you get feedback on that, incorporate those ideas into your proposal. And the third step is read other people's proposals. Then read the comments and the discussion that's happening and add your voice to it. This is the process by which we make all of the changes to the Go programming language. Eventually, through this refining process, the ideas will be ready, and we will ship them. I'd like to give additional insights into this part of the process and how it works. This is where principle 3 of consensus-driven design comes in. First, I'd like to start by dispelling a myth that I've heard from several people. The myth is that there's a small group of people at Google who decide all the changes that go into the Go language. The truth is, consensus happens among commenters. I'd like to share some other truths. The first is, most proposals are very, very small. The second is, nearly all proposal discussions reach a consensus among participants, which are the commenters on the thread. And the third is that the proposal review committee mostly does gardening. We've recently started publishing the minutes from our meetings. You can see that it's not very glamorous work. Most of the issues, we comment, asking clarifying questions, or do nothing and let the conversation continue. We also think about who's missing from the conversation and invite them to it. We close a small number of them when the discussion seems to have settled, either pro or con. Let's look at a recent proposal. This is just a random one from the pool of recent proposals. But there's some few interesting things about it. The first thing I think is interesting is it's got a good amount of participation. There's 25 comments from 9 participants. The second is that it starts by referencing user issues, which anchors it in experience. And the third interesting thing is as you can tell from the thumbs up and down that there's not consensus on this. But over time, and as the ideas are discussed and refined, it became clear that there was general consensus. It was marked as likely accept, and a sufficient window will be left open for anyone to provide reasons why we shouldn't accept it. Here's a set of recently reviewed proposals. You notice that each of them reference earlier comments and suggest an outcome based on those comments. In the proposal review committee, typically one person has the role of leaving comments, but is typing on behalf of everyone who's in attendance. Russ is usually one who volunteers for this, which is why they all have his name on them. Most of the time, the window goes by without any additional comments. But we feel this window, while rarely used, is essential to the process of establishing consensus. I want to share a recent example of when that window was used. The issue looks similar to the other ones we've seen. However, in this case, we misunderstood the situation, and Brian commented as such. And the issue was revived. The label was removed, and the discussion is ongoing. I also thought this was an interesting one from the recent ones. It starts as a fairly broad proposal. What they're trying to do here is add to strings a factory to convert bytes to strings, and they provide a good reason for doing so. However, in review, it became clear that there was one narrow use that was very impactful to common operations like JSON encoding. A separate, narrower proposal was filed for that. The broader one was eventually closed, but the more focused one has a lot of discussion on it and is still being discussed. Through all of this, you can see that changes happen slowly. And that is by design. It is a slow, careful, methodical process to ensure that we end up where we want to. And so while Go changes slowly, it's growing quickly. And I'd like to walk you through some of the major milestones of the past 10 years. So first, we start in 2009. That's the year Go is open sourced. The Gopher is born. And Go moves out of an experimental status at Google. In 2010, we received 2 awards, the Tyobe Language of the Year Award and the Bossy Award. Also in this year, append is introduced. For anyone who's used Go, it kind of feels like that's always been the language, but believe it or not, that was added in year 2. Also that year, we introduced Go Tour. 2011, GCC Go is merged into the main trunk of GCC. Go Fix is introduced, and YouTube adopts Go in production. In 2012, it was a banner year. Go 1.0 was released. The compatibility problems came along with it, and Google put a production service written in Go into production for the first time. 2013, we had some big programs written. Packer, Docker, and Hugo were all written in that year. We also introduced the 6-month release cycle, and the first Go conference was held in Tokyo, Japan. In 2014, Kubernetes came along. We switched from Mercurial to Git, and we had the first US and European conferences. And this year, we hit 500 contributors. And the pace really starts picking up. In 2015, the compiler was rewritten in Go. The garbage collector was rewritten to run concurrently. Women Who Go and Go Bridge were born. We had our first Indian and Chinese conferences. In 2016, HTTP2 and Context were introduced. We had our first Latin America and Middle Eastern conferences. For the first time, Go was awarded a top 5 most loved language by the Stack Overflow survey. We also held our own first user survey, and we reached 1,000 contributors. In 2017, we find that garbage collection pause times have been reduced to under a millisecond. We introduced type aliases, our first major feature change to the language. And Go was awarded for the first time the #1 language that developers wanted to use. And this year we had 13 conferences, and we held our first contributor summit. And last year, we introduced Go modules. For the first time, we had more contributors from outside of the Go team than inside the Go team. We've reached 19 conferences worldwide. We introduced a new brand and logo. At this point, Go is the #4 language used on GitHub by pull request. And developers said it was the #1 language they intended to learn. And in this year alone, we've already launched the Go Developer Network. We have 28 conferences worldwide. Our 2 releases contain major performance and memory reduction. We launched the Go module mirror and the checksum database, and we reached 2,000 contributors. Let's take a little bit more of a look of what's happening around the world now. The JetBrains survey is used to catalog how many people are using a variety of programming languages. In 2017, Go had a market share of 8%. By 2019, that had grown to 18%. It also was awarded the most promising programming language. It also had the #1 language was the #1 language that developers intended to switch to over the next year. Major companies are beginning to adopt Go for major things, and they're beginning to talk about that. And so just in the last couple weeks, Salesforce published that they ditched Python for Google's Go. Medium uses Go to run their entire social graph. And Twitter runs 5 billion sessions a day through a Go program. Our Reddit community, where most people say that they get news about Go, has been growing rapidly over the last several years, and it now reaches over 90 million members. And the Go developer network is not far behind with 83 million members. Thousand members. That would be crazy. Let's step back. That's 90,000 members and 83,000 members. I did that when I was practicing like 4 times. So thank you for catching that. All right. Wouldn't that be a trip? We'd probably be a much bigger room. All right. So what's next for Go? And partly we don't know. Our process is driven by you. All of us do this together. And we don't really know where we're going, but we do know a few steps ahead. So first is that Go is turning 10 on November 10th. And we've got our official hashtag, GoTurns10. And we're planning celebrations all over the world for this. And I think there's going to be one that they're going to tell you about more tonight. We're also launching the Go survey in the next few weeks. Beyond that, we hope module adoption continues across the world, across our ecosystem. And as people use it, that they file bugs and we continue to polish the experience. As Ian talked about at GopherCon this summer, we've been working on generics for several years, and we're continuing to work on that. We're also doing lots of user research. Myself and our user researchers and our engineers have been talking to individuals, to startups, and to enterprises, and we're trying to learn more about what makes you want to use Go, what challenges you have. And we're going to be working on improved tooling. A big part of that is Go Please, which is going to be launched in the next several months here for their 1.0. Okay. Ian said yes, so. All right. So part of that is I've been talking to lots of different companies, and I'd like to share with you some of the themes I've been hearing. These are pretty consistent across all the companies I'm talking to. Big companies, whenever I've talked to them, they have 2 questions, and it's almost universal. They want to know who else is using Go, and what else are they using Go for? And to date, we've not done a very good job of answering that question, but we're working on it. We're working on having really good answers to these questions. We also found that at most of these companies, they view Go as a modernizer. A lot of them are trying to move to the cloud or move to microservices. They're taking their old stack and they're trying to apply it in these new environments, and it's working disastrously. They're having really expensive things. Java is not built to run microservices, and they're often having in very large sums of memory. And so we have lots of stories as we're talking to companies where they take their old Java things and they switch them to Go, and they're experiencing 50 times cost reduction. Just phenomenal stories. And we're working on trying to help tell those stories better. And so now it comes to what Go's legacy. There is no time machine to the future. The future arrives slowly and unexpectedly. We don't know what will happen for Go or in the whole world, but we do know what mark we'd like to leave. We would like Go to be leaving a legacy of innovation. Go brought innovative ideas like Go routines, channels, simple interfaces to a mainstream audience. These ideas are now showing up in other languages, and we're excited for that trend to continue. Go Thumped was very controversial when it was first introduced in 2009. Now most languages have adopted a similar approach. Perhaps our most impactful legacy will be that we've inspired people to challenge established norms and look for inspiration everywhere, as Go has. We'd like to be leaving a legacy of empowerment. Go has made it possible for developers to be able to write production server software without the added expertise required by C and C++, without the complexity of modern Java, and without the performance cost of interpreted languages. More than any other language, Go empowers people to take their ideas and make it into a reality. I personally felt this when I first started writing Hugo, and that's what really attracted me most to Go. Others felt similarly empowered and have spoken at this conference about their creative uses of Go, including Florin's workshop on home automation, Ron's robots, Elias's GUIs, etc. Go changes lives. I've had the privilege of traveling around the world, and every place I've met men and women who often, without CS backgrounds or degrees, have been able to learn Go and use that to start companies, get better jobs, and improve their and their families' lives dramatically. Peter Stropel wrote that legacy is not leaving something for the people, it's leaving something in the people. In short, we are the legacy of Go. We are shaped by the history of what came before, and we get to be shaped in turn. Thank you.